Hello, everyone. So, back for Chapter 3, Part 1. So, Chapter 3 is about linear motion. And so, we're going to be looking at relative motion, speed, velocity, and acceleration. And then the second part of the chapter, we'll look at free fall and how far and how fast things fall. Okay, so what is relative motion? It sounds a lot like relativity. And in fact, relativity, I don't know what's wrong, sorry. With relativity, what Einstein was talking about was the idea that there is no center to the universe that you can measure things from. Everything is moving, everything is relative to everything else. And so we don't think of a center of the universe, even if we think the Big Bang occurred in one place. The universe has been expanding. It may or may not have an end. And so you measure things relative to other things. So when we are measuring the speed of the Earth that we talked about before, and it was 107,000 kilometers per hour, we were measuring that in terms of the sun, relative to the sun. The sun itself is moving quite fast. We're moving towards around our galaxy, the Milky Way galaxy. And we make a full trip around the galaxy about every 250 million years. So we've done it quite a few times. The sun is about, wow, where'd that knowledge go? Our sun currently is about 4.5 billion years. And so it's done it about 16, 17, 18 times. Our sun has circled around the Milky Way galaxy. And so we've been circling the Milky Way galaxy, but the Milky Way galaxy itself is moving at a high rate of speed towards the Andromeda galaxy. And in about 4 billion more years, we're going to collide with the Andromeda galaxy. So anyway, there's nothing out in space that is constant. Everything is moving. And the stars that you're seeing now, they've been moving since that light left them. So when you look out at the stars, they're actually in different locations. Okay, so relative motion is that idea that we just have to measure relative to something. So that's why in the lab we say that the lab is not moving. We know the Earth is moving, but we tend to say the lab is at zero speed because that's the easiest thing for us to do. We don't want to add 67,000 miles per hour to every measurement, right? And so here we've got a camera that's following this balloon person. And as he tracks the person with the balloons, you can see how other people are moving relative. And only these people are walking, and this bicyclist seem to be moving in the same direction at the same speed. So when we measure speeds here on Earth, we're measuring relative to the Earth and pretending that it is standing still. And we already talked about how ancient peoples were worried about the idea that the Earth could be moving, and how Galileo's idea of inertia, the fact that this crow can keep up with this moving Earth. So the crow doesn't have to flap its wings so it can fly at 107,000 kilometers per hour. It's already born with that motion, and inertia keeps it moving. So inertia is that resistance to a change in motion. Okay, now Galileo, who was so great about so many things, he is really considered the first person who tried to measure speed. So if you can imagine, people usually didn't give us speed. They would say, okay, well, I'll be there tomorrow. Or I'll be there by sunset. Or this horse can go from here to the next village in an hour. They didn't really have that idea with numbers that we have for speed. And so Galileo is really the first person who said, hey, let's really measure this. And so speed is equal to distance divided by time, which of course is where you get miles per hour. And in this class, we're going to be using meters per second primarily. So meters per second. And again, the conversion between those two is pretty easy. Meters per second, you just double it to get miles per hour. That's an easy way of thinking in your head, how fast is something going? So let's say you drove to get your new Xbox. And let's say you had to drive 15 miles. And you did that in, well, a quarter of an hour. So all right, so 15 divided by a quarter. Well, we're going to talk about fractions at some point when we're doing some problems. But 15 divided by a quarter, that would be 15 divided by 1/4. And of course, what do you do with a fraction? You invert it, you multiply by the reciprocal. So it's going to be 15 times 4/1. And so this person was driving at 60 miles per hour. Okay, so pretty fast, racing to the store to get your Xbox X Series. Okay, so I know all about that. Okay, so anyway, so here you are roaming at 60 miles per hour. Now, meters per second, of course, is easier because we don't have to deal with hours and minutes and things like that. So we will mostly, of course, be using meters and seconds because this is a science class, and that is scientific. All right. Now, there is a difference between what's called average speed and instantaneous speed in physics. And having said that, in this class, we're not going to be that fussy about it. But average speed is where you take a total distance covered and divide by that large time interval. So just like I did that one, that was a large time interval. Okay, a quarter of an hour is pretty big. Now, so you drive to grandma's house and you drive to grandma's house, and let's say grandma's house is 50 kilometers away, and you do that in 2 hours because you're driving very carefully and it's beautiful scenery. So what's that going to be? 25 kilometers per hour, which is pretty slow, actually. Okay. So, but usually we're not going to be using large distances like this so much. In physics, we're studying what's happening in the instant often. And instantaneous speed is the speed measured over a very tiny time interval. So, so it might be 1/10 of a second. And so what you're trying to get is, you know, when you went to grandma's house, sometimes you stopped, and you know, maybe that's why it took so long, is because actually you were having to wait in line to cross the bridge. You know, it was a drawbridge, and you stopped for a cup of coffee at the Dunkin' Donuts, and then you you were just driving along looking at the scenery. So anyway, so it took you a while. You weren't going the same speed the whole time. It was just an average speed. But instantaneous speed is trying to get at the meat of what is the speed right now. So you measure it over a tiny time interval. So that might be 2 seconds, it might be 1 second, it might be 1/10 of a second. But the idea is that you're not covering up you're saying you want to get the speed right then before it changes. Okay, now, so if you've got a car, okay, you may be familiar with the speedometer. And the thing is, does the speedometer try to measure average speed or instantaneous speed? Well, of course, it is measuring closer to instantaneous speed, right? It's trying to tell you the speed right now, not your average speed over the trip. And so, of course, which one do you get a ticket for? your instantaneous speed, right? So you can tell a policeman, hey, I was held up back there for a long time in a traffic jam. And so then I had to speed a little to make up. And so my average speed is still below the speed limit. But the policeman's not going to fall for that, right? Because it's the instantaneous speed that is going to get you killed. Okay, so anyway, so yeah. And sometimes you'll have a secondary speedometer in your car that is based off GPS. And that one often is a little bit different than your car's one, because often it is measuring from, of course, the satellite position. And so it's measuring usually over a larger time interval. Okay, now, so as I said, meters per second to miles per hour, you pretty much just have to double the meters per second. So here's 6 meters per second equals about 12 miles per hour. Okay, and but it's kind of the other way if you're trying to go to kilometers per hour. Actually, it's like you doubled the miles per hour. So yeah, so when we were saying that somebody was going around 50 kilometers per hour, then that's only about 30 miles per hour. Okay, but yes, usually we're just using meters per second and miles per hour. We're hardly ever using kilometers per hour in this book. They try to keep things simple. But your car, of course, has a kilometers per hour conversion on it. So usually your speedometer has kilometers per hour too, just in case you take it over to Europe or Canada or almost anywhere else in the world, because almost no one uses the British system nowadays. Okay, now another thing in physics, we have a difference between velocity and speed. And again, we're not going to get that fussed about it in this class. So usually I'm going to use the words interchangeably, whereas in a higher level class, you would have to actually, it makes a difference which one you're asking for. Okay, so velocity has both a magnitude and a direction. So this is a vector quantity, like a force, where I said we could do it as an arrow, and it could add up like arrows. So velocities can do the same thing. So you can have an airplane trying to go in one direction with a certain speed, but there's wind pushing the other direction. Well, those two can be added vectorially, okay, or subtract because they're in opposite directions. Or you can have an airplane that has a following wind, which I can't do with this arm. Okay, so the wind is pushing it along, a tailwind they call that, and that makes for fast trips. Anyway, so when you see something like 30 meters per second, that's the magnitude. That's how strong it is. Okay, what the magnitude or value of it is. And then the direction would be something like north or south or east or west. Something to indicate the direction, X, Y, Z, or at an angle of 45 degrees. So anyway, so something to indicate the direction. Now, in this class, we mostly are not worrying about that too much. But we'll say velocity, but give you something that doesn't really have a direction. Okay, so don't get too upset about that. It's just the way things are. When this book is trying to make things simple. Now, so anyway, so velocity is a vector, but and because of that, like we talked about with forces, a negative velocity just means the other direction. There's nothing bad about it. It's not any different, except it is in the other direction, and therefore it will cancel out, right? So yeah, so if you've got that airplane, oh, here comes drawing skills. It's not a bad airplane. Okay, so if the airplane is going at 300 meters per second to the west, and there's a tailwind of 80 meters per second, well, then those two are going to add up, right? So the total velocity of the plane is going to be 380 meters per second. Okay, so they add up like vectors, like forces. Now, when we look at speed, speed for a scientist just has a magnitude. We don't connect a direction with it. And so that's what we call a scalar. And so something like, and we would just write it like 30 meters per second, no direction. So some things are vectors, some things are scalars, and there was a little bit of that in the metric system review that we didn't do. I should probably bring that slide over this way. But the idea is that some things are vectors like velocity and acceleration and forces, and some things are considered scalars like mass and time and speed. Okay, so they don't really have a direction. Mass doesn't have a direction, but a weight does. We'll get to that in the next chapter. Okay, so mass and weight are not the same, as we talked about in the metric system review, and one is a vector and one is a scalar. Okay, so the formula for velocity, then we're also going to use as the formula for speed. We're pretty much going to always use V for velocity because it's a lot easier to write. If you write S for speed, it just looks like a 5. So anyway, so we're going to use velocity equals distance divided by time. But it's okay if you don't have a direction. That's all right. We're just going to continue to use it. Okay, so we don't have a separate equation for speed. All right, so we're just saying they're equivalent. So you can also think of this as speed equals distance divided by time. All right, so they are the equivalent for this class. Anyway, and so let's say you, we already did this, but you're going to grandma's house and it was 50 kilometers away, but this time, let's put this into meters per second. Okay, so we said that it took a quarter of an hour, which was 15 minutes, right? So when we have 50 kilometers, that's 50,000 meters, right? Because it's 1,000 meters per kilometer. And 15 minutes, well, we're not going to want that in minutes. We're going to want that in seconds. So, of course, you want to go 15 times 60. And so 15 times 60 is going to be 900, I believe. Okay, so now we're going to get this in meters per second instead of kilometers per hour like we did last time. And let me grab my calculator. Okay, so 50,000 divided by 900. And comes out to about 55, whoa, is that right? 0.5 meters per second. Yeah, that's about right. Okay. Hold it. What did I do differently? I'm sorry, I'll have to erase this there. So 50 kilometers. Oh, 2 hours. 2 hours. That's right. It was the other one that was a quarter. It was like, this person's going 100 miles per hour. See, that's the thing. We knew the person was going slower. Okay, sorry about that. So it was 2 hours. Oh, great. Okay, sometimes mistakes happen. All right, so let's just erase it, not hide it. Erase it. Erase this. It's a good idea to go back and verify your data. Okay, so it was over 2 hours. And 2 hours, of course, would be 2 times 60, which would be 120 minutes. Now we're going to multiply by 60, and now you can see this is going to be a much bigger number there. So 60 times 120, it's going to be 700, 7200, I believe. Yeah, it is. So 50,000 divided by that. And we got ourselves yeah, 6.9. Okay, that makes more sense because we said that he was going slower. Okay, so all right. So 6.9, double it. He's only going about, 14 miles per hour on average. Okay, so anyway, so speed is distance divided by time, and we're going to play around with the units, but not very much. So you're hardly ever using kilometers per hour. Okay, now we can turn that equation around. It was velocity is distance divided by time. So what if we want to find the distance? Well, distance is equal to velocity times time. And usually at this point, I ask my students, what is wrong with this picture? And someone knows. This guy isn't wearing a helmet. Okay, why do you want to wear a helmet? Because it may save your brain. It may not save your life, but it quite possibly will save your brain. So when they made a helmet law in California, there had been a lot of young men, mostly in hospitals, who had brain damage because they didn't have a helmet on. And you hit your head once, that can be it. You can get brain damage. And what happened was when the helmet laws went into place, all of a sudden, this pool of young men with brain damage dried up. Well, that actually made a spare parts shortage because a lot of times the brains were so badly damaged that these young men were donating their organs. Their parents were. So anyway, so suddenly having a helmet law made a huge difference in the spare part division. So do have a donor card, but yes, anytime you see someone without a helmet, you basically should be saying, why, thank you for your donation. Okay, so wear a helmet when you're out. Okay, so distance is velocity times time. So let's say that this guy is going at about 30 meters per second. So his velocity is 30 meters per second. And let's see how far he goes in 2 minutes. Okay, so our time is going to be 2 minutes. All right, so is that fast? Yeah, that's kind of fast for a motorcycle. 30 meters per second, just double it. It's about 60 miles per hour. Okay, so we're going to put this in here, right? 30 meters per second. That looks like a 6. And are we going to just put 2 minutes in here? No, because we want to have agreement between the units. So if velocities have seconds in it, then we definitely want the time to have seconds also. Okay, so this one's pretty easy though. So we're going to get 30 meters per second times 2 minutes is 120 seconds. And so 30 times 120, do I have to run to my calculator for this one? No, because you can use the associative properties and commutative properties of math that you've probably forgotten. But the idea that I can go 3 times 12 is 36. And then I can just add my zeros on. Right? So one of the things when you're doing these problems is it's going to help you review your math. It'll give you better skills. Now you're actually using them. Okay, so the seconds, cancel the seconds. and all I'm left with is meters. And again, when you are doing a problem, you should expect that the units will come out correctly. You put in the correct units, and you'll get out the correct units. Okay, so for distance, it always is a length, which should be in meters usually. Now, for those of you who have had higher level physics classes, you may have noticed that that equation was part of another equation. So you may have had an equation before that is something like x, representing distance, equals x0 plus v0t plus 1/2 a, the acceleration, t squared. Okay, so this is the equation you would get in a lot of physics classes. However, what Hewitt did is he takes separate little pieces and simplifies it down. So when you're looking at this equation, what it is maybe you've got a starting distance. Well, Hewitt says, no, everything starts at 0. So we don't have to worry about the starting distance. And for other equations, you might be gaining, other situations, you might be gaining speed because it's accelerating. And Hewitt's like, no, it's either constant velocity or accelerating, but not a combination of things. So anyway, so this one we don't need either in this part. And so he's just shortening it down, and instead of x, it's called distance, to just v0t. But yes, when you look at one of those equations, you should be able to look at it and say, what is this saying? It's saying you're getting a little bit of distance from the original. You're getting some distance from the fact that it's moving at a constant speed, or it had an original speed. And then you're also getting distance from the acceleration. So when you go to a higher level class, look at your equations and break them down. But Hewitt has done that for you. And so we just have to use this shorter equation. Okay, now, changing velocity, because remember velocity had a magnitude and a direction, it was a vector. That does mean there is a difference in that you can change the speed, the magnitude, or the direction, and they both will be counted as a changing velocity. Now, we're only going to use that later when we reach the chapter on circular motion, but it is something to be aware of. So speeding up, slowing down, you obviously know those are changing velocity, but changing direction, that's also considered part of it. Okay, so because a velocity is a vector. And so you can actually have a constant speed. So if this car is driving around this circle at a constant 15 meters per second, which is pretty fast for a circle, then his speed may be a constant, but the velocity is changing because the direction is constantly changing, right? Okay, so let's talk about acceleration. Acceleration, the formula for that is that acceleration is the change in velocity divided by a time. Now, one of the important things to understand is that acceleration can be considered a positive and helps you to speed up. And that's how most of us think of it. You know, we press the accelerator in the car, right? And acceleration is also a vector, so you can represent it by an arrow. So over here, I've got a V for velocity, and that's a red arrow. And then I've got A for acceleration, and that's a blue arrow. And the idea is that the car is going to speed up if those are in the same direction. And you're like, obviously they're in the same direction. Well, that's right, they are. But sometimes people have trouble with the idea of deceleration. Remember, in physics, you can just think of that as a negative. It's going in the opposite direction. The opposite direction to what? The opposite direction to the velocity in this case. And what it is, it's like when you put the brakes on. Your car is trying to go west and you decide to slow it down. What that actually means is you're decelerating. You're applying an acceleration in the opposite direction. So a deceleration is just opposing the motion. So the car is going to slow down just as much as the other car was speeding up. So this one, it would keep adding to it and it would get faster and faster and faster. This one, slowly, it would get less, right? The velocity would get less because the acceleration is the opposite direction. Okay, so you can think of a deceleration as a negative acceleration. And again, that mostly means other direction. Okay, now the formula for acceleration, change in velocity over time. Let me show you this cool symbol. This triangle, which is a delta, Greek delta letter, is used in physics to mean change in. And change in is always going to be defined as final minus initial. So we're saying delta V, which means change in velocity, and that's going to be the final velocity minus the initial velocity. So anyway, it's a really nice shorthand to be able to say delta V, because it's much shorter than saying change in somehow. Anyway, so it's certainly much shorter to write. Okay, so anyway, so you will see me use delta V, delta T. It'll come up in various things, and it always means change in. So delta T would be change in temperature. We'll see that a lot when we reach the heat chapters. All right, so let's calculate some accelerations. So here we've got a car that's speeding up from 10 meters per second to 30 meters per second, and it's doing that in 5 seconds. Okay, so this is an acceleration, right? It's speeding up. So we're going to figure out our acceleration, the change in the velocity divided by the time. And so that's going to be V final minus V initial divided by the time. And of course, so when you're reading a problem, you've got to identify these things. So initial velocity, that must be the 10, right? That's V initial. And the final velocity must be the 30. And of course, this is the time. All right, so V final minus V initial. And so we know we're going to take 30 meters per second minus 10 meters per second and divide by 5. And so we're going to get 20 divided by 5, which is going to be 4. Now, let's look at the units there. Let me get rid of that T, which is in the way there. Okay. All right. So what are the units? Well, we have meters per second, and the 5 is in seconds. So our final set of units can be written as meters per second, because that's the idea of an acceleration. You're changing the speed by 4 meters per second every second. Now, if you've been in another physics class, you know it's easier, and often people just write 4 meters per second squared, which is mathematically the same thing. But Hewitt does like to emphasize the fact that it's saying your change is 4 meters per second every second. Okay, so what does that mean? Well, if you had a car, this car, and it started out at 10, after 1 second, it would be going 10 plus 4, right? It would be going 14. That's what the meaning. It gets 4 meters per second every second. So 1 second after that, it would be going 14 plus 4, 18. Another second after that. And 18 plus 4 would be 22. Another second after that. And 22 plus 4 would be 26. And finally, after 5 seconds, 1, 2, 3, 4, 5 seconds, it's now going to be at 30. Right? So that's the idea, is that you are gaining a little bit of speed every second, and that adds up. Okay, now the second part of this problem is the car sees that he has to stop, and he goes from 30 meters per second to a stop in 5 seconds. Okay, we're going to use the same formula. The acceleration, change in velocity over time. And maybe in your head, you're already going, okay, 30 minus 0, right? Well, let's double check on that. This is actually the initial velocity, right? And what's the final velocity? It's 0, right? It's coming to a stop. So that's one thing too when you're doing homework problems. Keep aware of words like starts from rest. That would mean the initial velocity was 0, or comes to a stop. That's where the final velocity is 0. Because they're not explicitly going to say the initial velocity is 0. They've given it to you in words. Okay, that's one reason people hate story problems sometimes. But that's what you have to get the hang of. Okay, and of course the time is 5 seconds. So what's the acceleration? Well, if we use the formula, v final minus v initial, divide by the time, final is 0, initial is 30. So if in your brain you were going 30 minus 0, you might have missed the fact that this is actually going to come out to be a negative number. Right? It's going to be minus 6 meters per second per second. Okay, so again, the negative sign there means other direction. This is a deceleration. The brakes are on. The car is going to come to a stop. And so the velocity was one direction, the acceleration is the other direction. But that's why you got to make sure you put the proper final and initial velocities, because otherwise you'll miss that negative sign, and therefore you'll miss the question on the test like this. Okay, so anyway, so what is this car doing? Well, it's starting out at 30. After 1 second, it's lost 6 meters per second. So it's going to be only 24. Then it's going to be 18. Then it's going to be 12. And then it's going to be 6. And finally, just in time for the stop sign, it'll be 0. Okay, so it's losing 6 meters per second per second. Now, remember we talked about rapid deceleration already. When you come to a stop, suddenly your body wants to keep going forward because your body is still trying to go at 30 meters per second. And so that's, again, remember to have your seatbelt on, or if you're on a motorcycle, make sure your helmet's on too, and slow down. Sometimes people think they're going to get thrown clear in a crash. Well, usually you're in a car where you have to squeeze through a window to do that, and people usually leave limbs behind. And quite often people get thrown out of a car and then the car rolls over on them. So don't think that's going to save you. Put the seatbelt on. Okay. All right. Now, one of your homework problems has a question like this. So when you reach it, you might want to ask questions about that. So that's what we're going to be doing a lot of on Tuesdays and Thursdays, is asking questions. So this is usually one that I go over, so don't feel afraid to ask about it. But it does relate to this chapter in that it has to do with velocities and whether the velocities stay constant or whether there is an acceleration that goes on. Okay, so you've got balls rolling down tracks. They have different shapes. You've got the same one in your homework. Okay, so that's the end of part 1. We'll get to part 2 Well, when you click on that dial. All right, so I'm going to stop lecture at the moment.